Before we even get started today, I just have to explicitly state right at the very beginning of this broadcast that this is an AI-generated analysis.
Yes. Definitely good to get that out of the way.
Right. So, imagine you are an engineer, right? You're wearing these augmented reality glasses, and you're working out on a remote, super hazardous oil rig.
That is a high-stakes environment.
Exactly. And suddenly, a critical pressure valve is about to burst. If the sensor data from your glasses has to travel to a centralized cloud data center like 1,000 miles away just to be processed and sent back.
Oh, that resulting 100-millisecond delay could literally cost you your life.
Yeah, it's terrifying.
Yeah.
So welcome everyone to a comprehensive analysis and detailed technical review of the core material from the book Edge Computing with Amazon Web Services by Sean Howard.
It is a fantastic resource.
It really is. And our mission for this review is to basically systematically examine the architectural strategies for deploying AWS cloud processing directly into the physical world.
Right, pushing it much closer to where the data is actually being generated.
Exactly. So today, we're going to move through the technical mechanics of near-edge and far-edge networking. We'll talk about completely disconnected environments, public 5G integration, and Industry 4.0 architectures.
It's a lot of ground to cover, but I think we really first need to establish the fundamental structural shift that's driving all of this.
Right, because edge computing is not just some marketing term anymore, is it?
No, not at all.
Yeah.
It's actually a forced disaggregation of centralized services.
Yeah.
You know, organizations are distributing their infrastructure because they're trying to overcome three basically immovable limitations.
And those are?
The laws of physics, the economics of data transfer, and the strict requirements of regulatory data sovereignty.
Ah, right. Physics is a big one. I mean, light traveling through fiber optic cables still has a fixed maximum speed, right?
Exactly. You can't cheat the speed of light. So by moving computational resources physically closer to the end user, or say the industrial machine, you completely bypass the inherent latency of sending data all the way back to a distant cloud region.
I like to visualize this architectural shift by thinking of a global corporation, right?
Yeah. So, yeah.
Well, imagine they delegate decision-making authority to regional branch offices. If every single minor transactional question has to be routed all the way back to the global headquarters, operations just grind to a halt.
Right. The bureaucracy alone would kill your efficiency.
Exactly. But when a local branch office can independently verify a transaction, the whole organization operates so much faster.
That's a really great analogy. But, establishing those localized compute environments introduces some severe network constraints.
Because they're basically out in the wild.
Yeah. When architects rely on the public internet to connect these near-edge outposts, they run straight into the bottleneck caused by the transmission control protocol.
TCP, right?
Yes, specifically the TCP receive window mechanism.
Okay, break that down for me. What is the receive window?
Well, the TCP receive window, or RWIN for short, dictates the exact amount of unacknowledged data a receiving server can accept before the sending server has to pause transmission.
So it's kind of like a buffer.
Exactly. And over long geographic distances, the physical limitations of the network introduce latency. As that latency increases, the TCP receive window quickly becomes a massive bottleneck.
Because the sender's just sitting there waiting for an acknowledgement.
Right. The sender spends way too much time just waiting for the receiver to say, hey, I got that. It results in drastically underutilized network capacity.
So wait, a company might pay for like a 10 gigabit connection, but only actually achieve 1 gigabit of throughput?
Yes, exactly. Because the protocol is artificially pausing the data flow. And to make it worse, standard internet routing introduces variable packet loss.
Oh, and TCP hates packet loss, right?
It really does. When TCP detects packet loss, it assumes network congestion and automatically triggers these congestion avoidance algorithms, which just reduces the throughput even further.
Wow. So how do we mitigate those constraints? I mean, modern networking must have solutions for this.
They do. First, organizations will establish private wide area networks to guarantee predictable routing paths. And then, at the network layer, they implement global server load balancing and IP Anycast.
I always found IP Anycast to be super fascinating.
It's particularly elegant, isn't it?
Yeah, because it allows multiple geographically dispersed servers to share a single identical IP address.
Exactly. So when a device sends a request, the network protocol automatically routes the traffic to the topologically closest node. It instantly reduces latency.
That's brilliant. And are aren't engineers also replacing TCP entirely in some cases?
Yeah, they're adopting newer protocols like HTTP3 and QUIC.
Oh, right, because QUIC operates over UDP, the user datagram protocol.
You got it. And because UDP doesn't require those strict sequential acknowledgement mechanisms that TCP does, it effectively eliminates head-of-line blocking.
So the data stream just remains continuous.
Precisely.
Okay, but hang on. Opening these regional branch offices, so to speak, that completely shatters the traditional security perimeter, doesn't it?
Oh, absolutely.
I mean, protecting a highly fortified AWS data center is fundamentally different from trying to secure a localized server rack sitting in, like, the back of a dusty retail warehouse.
It's a completely different ballgame. Moving from a centralized cloud to these distributed outposts demands a really rigorous approach to security parity.
So how do organizations ensure that parity?
Well, it starts with extending the principle of least privilege directly to the edge using AWS Identity and Access Management, or IAM.
Right, so locking down who can access what.
Exactly. But because these near-edge devices reside outside controlled facilities, physical device hardening is also paramount. You have to implement a hardware root of trust.
What does that actually look like in practice?
It involves embedding physical, tamper-evident cryptographic chips right into the edge device.
Oh, wow. So if someone tries to physically mess with it.
Yeah, if an unauthorized individual attempts to pry the physical casing open or load a rogue operating system, the hardware itself recognizes the breach and refuses to boot.
It just completely locks down.
It must automatically fail closed. And furthermore, the decentralized nature of these outposts mandates really robust remote monitoring.
Because if a device goes dark, you need to know immediately.
Right. If a device loses communication with the control plane, automated incident response strategies have to immediately quarantine that node to prevent any lateral movement across the corporate network.
Got it. Okay, so we've established the parameters for wired, reliable, near-edge networks. Let's push the architecture into environments where laying a physical cable is just impossible.
Ah, the far edge.
Exactly. The far edge is totally governed by the volatile mechanics of wireless protocols, and designing for that requires a deep understanding of radio frequency, or RF communications.
Architects really have to balance wavelength, modulation, and multipath propagation.
Right, because different frequencies behave very differently in the physical world. Like, lower frequency wavelengths penetrate obstacles like concrete walls really effectively, but they carry very little data.
And higher frequencies offer massive bandwidth, but they possess a very short range, and they tend to bounce off physical objects.
And that bouncing creates multipath propagation, right?
Yeah, where multiple delayed echoes of the exact same signal arrive at the receiving antenna, which severely degrades the connection.
So when evaluating wireless protocols to navigate those physical constraints, architects really have to map the technology strictly to the use case.
Absolutely. For example, 4G, LTE, and 5G networks are deployed for high-throughput, latency-sensitive requirements.
Right.
Conversely, low-power wide-area networks, like LoRaWAN and narrowband IoT, those are deployed for entirely different scenarios.
Like what?
Well, these low-power networks are specifically designed for battery-operated devices.
Mm.
Think of agricultural soil sensors out in a massive field that only need to transmit, like, a few bytes of data once a day.
Okay, but I have to challenge an architectural assumption that I see often made here.
Okay, let's hear it.
You can't simply take an application designed for a 5G network and just casually deploy it onto a LoRaWAN network, can you?
Oh, definitely not.
Right, because designing an app for continuous high-bandwidth 5G connectivity assumes a stateful, constant communication channel.
It assumes the pipe is always open.
Exactly. But an application utilizing LoRaWAN has to be fundamentally rebuilt to tolerate asynchronous, stateless data bursts followed by really long periods of absolute silence.
That's a critical point. The transport layer directly dictates the application logic. The application layer must absolutely be aware of the transport layer's physical characteristics.
It's all connected.
Yeah.
Speaking of connections, there was a really fascinating detail in the source material about how 5G far-edge networks are managed.
Oh, are you talking about the Global Navigation Satellite System?
Yes, GNSS. Most people, myself included, associate those satellites strictly with location tracking for navigation.
Like GPS on your phone.
Exactly. But the book details how 5G network function virtualization applications utilize these satellites to extract a highly precise, free atomic clock source.
It's so clever. Because orchestrating 5G radio frames requires microsecond-level synchronization across thousands of distributed nodes.
Right, and purchasing and deploying physical atomic clocks at every individual cell site is financially prohibitive.
It would cost a fortune. So instead, the edge devices use the timing signals broadcast by GNSS satellites for their network time protocol. It ensures perfect synchronization across the entire architecture.
That is just amazing. All right, so let's shift gears again. We need to examine environments where even wireless connectivity is actively denied or completely severed.
The hardest environments of all.
Yeah, these are classified as disconnected, denied, intermittent, and limited bandwidth environments, or DDIL for short.
The tactical edge frequently presents these exact conditions.
Right, the book uses the classic example of forward-deployed military command posts.
Yeah, because a military post cannot broadcast a constant network signal without exposing its physical coordinates through electromagnetic emissions.
Right, they have to operate in complete radio silence to eliminate the risk of hostile data interception.
Exactly. And to operate in these extreme environments, organizations deploy specialized hardware, like the AWS Snow family.
Now, devices like the AWS Snowball Edge possess a really crucial architectural distinction, don't they?
They do. They maintain their own local control planes and management planes.
Which is huge, right? Because in a traditional cloud deployment, if your connection to the internet is severed, you can't launch a new virtual machine or reconfigure your storage.
Right, because the control plane normally resides back in the centralized cloud region. But a Snowball Edge allows operators to launch compute instances, manage object storage, and authenticate users entirely locally.
That is wild, and they expose the exact same application programming interfaces, or APIs, as the standard in-region services.
Exactly. So a developer writes an application once using standard AWS SDKs, and that identical code executes seamlessly, whether it's deployed in a massive data center or an isolated tent in the desert.
So what does an advanced DDIL topology actually look like out in the field?
Well, you might combine a compute-optimized AWS Snowball Edge device with Amazon Elastic Kubernetes Service anywhere, or EKSA alongside a localized 5G core.
So it's basically a 5G network in a box.
Pretty much. That specific configuration supports roughly 100 independent 5G devices registered on a localized radio access network.
So you get a self-contained, high-bandwidth, private cellular network operating in a completely disconnected location.
It's incredible. Administrators can even automate the deployment of smaller edge units. Like you can set up an AWS Snow Cone as an IoT gateway using infrastructure as code tools like AWS CloudFormation.
You know, I always compare this DDIL architecture to a submarine.
Oh, a submarine. How so?
Yeah, well, the submarine operates autonomously in the depths, right? It gathers vast amounts of sensor data and executes its mission in a completely disconnected state.
Okay, I track with that.
But eventually, the submarine must surface to transmit its gathered intelligence back to command and receive new operational orders before submerging again. But here's my question. When the local edge device reconnects, the system faces a massive data reconciliation challenge, doesn't it?
It really does. It's a huge hurdle.
I mean, if a localized cluster has been disconnected for 3 weeks and suddenly has to synchronize hundreds of gigabytes of new machine learning training data back to the core AWS region, attempting to push all that data simultaneously would just instantly saturate the intermittent uplink, right?
It would completely crush the connection and probably corrupt the database.
Right. So how is that handled?
Resolving that synchronization challenge relies on differential synchronization protocols.
Differential synchronization. Oh.
Yeah, the edge device does not attempt a raw monolithic upload upon reconnection. Instead, it buffers the data locally on its internal storage.
Okay, so it holds on to it.
Right. And then it utilizes synchronization services, such as AWS DataSync, to systematically scan the local files and the cloud-based destination.
Oh, to find the differences.
Exactly. The service identifies the exact delta changes, only the specific blocks of data that have been modified since the last connection.
That is so much more efficient.
It is. It transfers only those newly modified blocks, and it applies strict bandwidth throttling limits to prevent network saturation.
What if there are conflicts, though? Like a record was modified both at the edge and in the cloud during that disconnected period.
That's a great point. Predefined conflict resolution protocols within the application logic automatically determine which data source acts as the authoritative record.
Makes sense. Okay, we need to shift gears from the rugged, disconnected tactical edge to the ultra-low latency requirements of public 5G networks.
Multi-access edge computing, or MEC.
Right, because when an application requires single-digit millisecond latency, routing traffic through the public internet is simply too slow.
Way too slow. AWS wavelength zones solve this by physically embedding AWS compute and storage hardware directly inside the data centers of global mobile carriers.
Like Verizon or Vodafone.
Exactly. By placing the resources at the absolute edge of the 5G network, the data never even touches the public internet.
Oh, wow.
Yeah, it travels from the mobile device to the cell tower, directly to the AWS wavelength zone sitting right there inside the telecom facility.
And that architectural placement facilitates those really complex, immersive experiences, right? Like the connected worker operating on the hazardous oil rig we talked about earlier.
Yes, perfect example.
That worker utilizes augmented reality glasses that overlay complex structural schematics directly onto their physical field of view. But rendering high-fidelity graphical data requires immense GPU compute power, which those lightweight glasses completely lack.
They're just displays, basically. So the application offloads the rendering process to the local AWS wavelength zone.
And the wavelength server renders the schematics and streams the finalized visuals back to the glasses with imperceptible delay.
Exactly. Similarly, developers can render high-fidelity virtual reality gaming environments using pixel streaming tools like Nice DCV and Unity.
The heavy computational rendering occurs at the carrier edge, while the user's headset only receives the lightweight finalized video stream.
It's a game changer for latency.
It is, but I have to point out a potential architectural risk here.
Okay, what's your concern?
If AWS wavelength zones are physically tied to specific global mobile carriers, doesn't that fragment the application deployment?
It definitely fragments it.
Right. I mean, if one user is on carrier A and another is on carrier B, directing them to the correct local server must complicate load balancing immensely. Managing traffic via Route 53 seems nearly impossible when users are on entirely different walled-off telecom provider networks.
That is a very valid concern. But the architecture addresses this fragmentation by integrating deep routing intelligence directly into the domain name system.
Oh, so Route 53 handles it automatically.
Yes. Route 53 is specifically configured to recognize carrier IP address bases. Yeah, when a mobile device initiates a DNS query to find the application, Route 53 analyzes the source IP address. It dynamically detects that, hey, this specific IP address belongs to the Verizon network rather than the Vodafone network.
And then it routes them accordingly.
Exactly. Route 53 resolves the DNS query, explicitly returning the IP address of the application instance deployed within that specific carrier's wavelength zone.
That's brilliant. So the application architect must provision infrastructure across multiple different carrier zones, but the immense routing complexity is entirely abstracted away from the end user.
Exactly. The dynamic DNS resolution handles all the heavy lifting.
Awesome. Well, as organizations synthesize these individual edge deployments into a unified, globally distributed edge architecture, the sheer scale must become incredibly daunting.
Oh, the scale is massive.
Yeah.
But the AWS Global Network supports this by leveraging Amazon CloudFront.
And CloudFront Embedded Points of Presence, or POPs, don't merely act as simple storage caches for static images anymore, do they?
Not at all. They operate as serverless compute environments directly at the network edge.
Which means they can execute complex logic.
Yeah, intercepting, authenticating, and even heavily modifying user requests before those requests ever reach a centralized database.
But, you know, as edge infrastructure scales from a few centralized cloud regions to thousands of localized compute nodes spread across factories and telecom centers, relying on manual configurations becomes impossible.
Mathematical impossibility.
Human error will inevitably lead to catastrophic configuration drift, right? Where individual nodes slowly diverge from the approved security baseline until a breach occurs.
Managing that vast scale makes infrastructure as code a fundamental operational requirement. You just can't do it manually.
Right. The reviewed material details deployments where HashiCorp Terraform is utilized to orchestrate infrastructure across multiple geographic planes simultaneously.
Yes. An architect executes a single Terraform script, and the pipeline automatically deploys the heavily secured core database within a standard AWS region, provisions the latency-sensitive application tier within an AWS local zone,
And establishes the mobile-facing rendering interface within an AWS wavelength zone all at once.
Exactly. This level of automated orchestration is absolutely mandatory to support the business drivers of Industry 4.0.
Right, because the massive increase in robotic industrial automation demands decentralized processing just to maintain continuous factory operations.
And don't forget the strict data sovereignty regulations. They legally mandate that citizen data be processed entirely within specific national borders, which further accelerates the adoption of these distributed architectures.
So to manage all this structural complexity, architects rely on the AWS well-architected framework, right?
Yes, the framework is derived from traditional enterprise architecture standards like Zachman and 2GF. It provides explicit design patterns.
It allows engineering teams to systematically scale their edge compute demands over the coming decade, while actively avoiding documented anti-patterns that lead to system failure.
Exactly. It's a vital blueprint.
Well, as we conclude this comprehensive analysis, you can see how this architectural shift spans deep physical infrastructure, complex radio frequency physics, and highly advanced cloud routing protocols.
It's all coming together.
The cloud is no longer confined to massive centralized facilities. It is literally bleeding out into the physical world.
You know, it really makes you consider the cyclical nature of computing models.
What do you mean by that?
Well, think about it. Decades ago, technology centralized processing power within massive mainframes.
Right.
Subsequently, the industry distributed that power outward to individual personal computers.
Ah, I see where you're going with this.
Yeah. Following that era, the industry shifted back to the highly centralized cloud computing model, consolidating resources into massive data centers again.
And now, driven by the physics of edge computing, we are distributing processing power outward once again, pushing it to the very perimeter of the network.
Exactly. Which raises a fascinating question for you to consider.
Mm-hmm.
As intelligent devices proliferate, what will the ultimate equilibrium between the centralized core and the distributed edge look like in the next decade of infrastructure design?
That is a phenomenal thought to end on. We strongly recommend that you read the actual book, Edge Computing with Amazon Web Services by Sean Howard, to gain full access to the Terraform and CloudFormation deployment templates we discussed today.
It is definitely worth the read.
Absolutely. Thank you for joining us, friends of the show. We encourage you to subscribe for future comprehensive technical reviews. Have a great day.